In the 16th century, a Polish astronomer named Nicholas Copernicus challenged the long-held belief that the Earth was the center of the universe. Until this time, most people believed in the geocentric model of the universe, where the Earth was stationary at the center and the sun, moon, and stars revolved around it. Copernicus proposed a radical alternative, the heliocentric model. He argued that the Earth is not stationary, but instead revolves around the sun, along with the other planets. This simple yet revolutionary idea marked a turning point in our understanding of the cosmos. The heliocentric model provided a simpler explanation for the observed motions of the planets, particularly the retrograde motion of Mars, which had puzzled astronomers for centuries. Copernicus's ideas, while not immediately accepted, laid the groundwork for future scientific discoveries. His work sparked a revolution in astronomy, inspiring other scientists to question established theories and search for new explanations. This shift from an Earth-centered to a sun-centered view of the cosmos paved the way for a deeper understanding of gravity and its role in the universe. Copernicus's work was not without its flaws. He still clung to the idea that planets moved in perfect circles, an assumption that would later be corrected by Johannes Kepler. Nevertheless, his heliocentric model represented a paradigm shift in astronomy, paving the way for a new era of scientific discovery. Following in Copernicus's footsteps was Tycho Brahe, a Danish nobleman known for his meticulous astronomical observations. Brahe dedicated his life to making precise measurements of the positions of stars and planets, achieving an unprecedented level of accuracy for his time. He built his own observatory, Uraniborg, equipped with the most advanced instruments of the era. Brahe's most significant contribution was his detailed observations of Mars. He tracked the planet's movement night after night, carefully recording its position in the sky. These observations, made without the aid of a telescope, were incredibly precise and would later prove invaluable to his assistant, Johannes Kepler. Brahe's passion for accuracy was legendary. He even lost part of his nose in a duel and wore a prosthetic made of gold, silver, and wax. This dedication to detail laid the foundation for Kepler's groundbreaking discoveries. Brahe's observations, while impressive, were just raw data. It would take the genius of Johannes Kepler to transform these measurements into fundamental laws of planetary motion. Johannes Kepler, a German mathematician and astronomer, inherited Tycho Brahe's treasure trove of astronomical data. Kepler was convinced that there must be a mathematical harmony underlying the motion of the planets. He spent years painstakingly analyzing Brahe's observations, searching for patterns and regularities. Kepler's hard work paid off when he discovered three fundamental laws of planetary motion. These laws, known as Kepler's laws, described the elliptical orbits of planets, the varying speeds at which they travel around the Sun, and the relationship between a planet's orbital period and its distance from the Sun. Kepler's laws revolutionized our understanding of the solar system. He showed that planets do not move in perfect circles, as previously believed, but in ellipses, with the Sun at one of the two foci. This discovery shattered the ancient belief in the perfection of celestial spheres. Kepler's laws were empirical, meaning they were based on observation rather than a theoretical framework. It would take the genius of Isaac Newton to provide a physical explanation for these empirical laws. Newton's eureka moment, unifying heaven and earth. Isaac Newton, an English physicist and mathematician, is considered one of the most influential scientists of all time. In his groundbreaking work, Philosophiae Naturalis Principia Mathematica, published in 1687, Newton laid the foundations for classical mechanics, optics, and calculus. Newton's most profound contribution was his law of universal gravitation. Legend has it that Newton was inspired to formulate his theory after observing an apple falling from a tree. He realized that the same force that pulls the apple to the ground might also be responsible for keeping the moon in orbit around the Earth. Newton showed that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This simple yet profound law explained why planets orbit the Sun, why the Moon orbits the Earth, and why tides occur. Weighing the Earth, Henry Cavendish, and the gravitational constant. Newton's law of universal gravitation introduced a fundamental constant, known as the gravitational constant, denoted by the letter G. This constant determines the strength of the gravitational force between any two objects in the universe. However, Newton did not determine the numerical value of G. It was Henry Cavendish, an English scientist, who first measured the value of G in 1798. Cavendish used a torsion balance, a sensitive instrument that measures the faint gravitational attraction between masses. By carefully measuring the tiny deflections of the balance caused by the gravitational pull between lead spheres, Cavendish was able to determine the value of G with remarkable accuracy. Cavendish's experiment was a triumph of experimental ingenuity. It not only provided a numerical value for G, but also allowed for the calculation of the Earth's mass. By knowing the value of G, the radius of the Earth, and the acceleration due to gravity on the Earth's surface, Cavendish was able to calculate the mass of our planet. The universal law of gravitation, a force that binds the cosmos. Newton's law of universal gravitation, with the gravitational constant G, determined by Cavendish, stands as one of the pillars of modern physics. It explains the force that holds the solar system together, governs the motion of galaxies, and influences the evolution of the universe. The law states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses. The more massive the objects, the stronger the gravitational attraction between them, inversely proportional to the square of the distance between their centers. The farther apart the objects, the weaker the gravitational force between them. While the law is formulated for point masses, it also applies to spherical objects, where the distance between their centers is considered. This simplification makes it possible to calculate the gravitational force between planets, stars, and other celestial objects. Newton's law of universal gravitation is a testament to the power of human ingenuity. It demonstrates our ability to unravel the mysteries of the universe and formulate fundamental laws that govern the cosmos from the smallest particles to the largest structures.